the Metropolis and Metropolis tasting algorithm. This is just purely for fun, nothing going to be tested. So maybe you can relax. Yeah, I posted the slides on Moodle if you want to take a look. Also, some of the sample code there. All right, so this is from just an example. There are so many examples out there, but I was trying to use something sort of close to what we are doing. So this was one question from return 2, if you remember. It's a rash model, and then there are multiple parts of the question, and I asked you to derive some of the full conditional posterior distribution. And what we find out, I think, is U and P. You will be able to recognize what they are, the full posterior conditional distribution. The beta K, you cannot. Okay, it's very complicated there. And then, of course, you can say, okay, let's ask JAX to do it. And JAX will do it for you. But then what exactly is being done within JAX, I just want to talk about 2 important MCMC sampling techniques that is useful when you do not have recognizable full posterior conditional distribution. Okay, so first one is Metropolis. The other one is Metropolis tasting. So for the Metropolis, all right, so the general algorithm is like this. Suppose you want to estimate the parameter theta, okay, and it's posterior, so theta given y, and let's say it's a scalar at the moment. So you can start with the initial guess, like say theta 1, and then you can, of course, keep running it, but the way that you generate the next value works in this way. So first of all, you draw one possible value of theta from a symmetric distribution. We call it J. So it's conditioning on the previous draw. So it's theta S, that's what is being conditioned. We call it J because we call it jumping distribution, because we're going to use this throughout. And notice that I wrote it down here, but I think I should have highlighted when I was making the slides. It is symmetric. Okay, so symmetric is the feature of doing Metropolis algorithm. Okay, later when we move to Metropolis tasting, you can start to have unsymmetric. Okay, but this one is easier to work with, so let's think about the symmetric distribution. For example, like a normal. You sample it center at the previous theta value, right? And then you choose like yeah, I'm gonna have that square there, but you know what I mean, at the standard deviation with C. Okay. So let's say this is theta star. We draw one value from it. And the way that we're going to determine whether we're going to move to that value is through equation 2 here. So imagine, so now we're trying to, so the goal of learning MCMC is we're trying to use iterative step, iteration by iteration, to achieve to the posterior distribution of the unknown parameter. Okay, and we have seen those graphs before in trace plot and stuff. Sometimes they get stuck in some region and never get out, or like for easy samplers or like easy models, it's pretty easy to get a really non-sticky trace plot. But the general goal, if you think about like doing sampling in this way, especially now you have a new draw theta star, and you have to have some kind of decision rule that you have to use it to determine whether you should move to the next draw or not. Okay, and the way pretty naturally to think about it is to evaluate, say, in equation 2 that I'm writing down here, the posterior probability of this draw, of the new draw comparing to the old draw, right? So if it's more likely to be the old draw, then this ratio is going to be small, right? Because this ratio is what? It's P theta star given Y over P theta S given Y. So theta S is my current draw or my previous draw, let's say, and theta star is the current draw. Okay, so I'm trying to evaluate this, and then of course if R is large, then I have higher like belief or probability that I should go to this new theta star. Okay? So this is what we call the ratio, like the ratio that we use, and in particular by Bayes' rule, we know what if we want to evaluate the posterior of theta star given Y, then we can actually, it's proportional to the likelihood times the prior. Okay. So that's why in equation 2, the final step, you can see that we're evaluating the data, which is the likelihood under this new draw theta star, right? That's the data likelihood times the prior over the likelihood under the current draw times the prior of the current draw. Okay, so I think this is, I mean, hopefully it's intuitive. You were making decision of whether you should move to the new draw by evaluating whether the data is more likely, or I should say the posterior is having a higher probability than the current draw. If it's higher, you're going to move because eventually that will be where the posterior is. If it's lower, you might want to stay. So if you imagine here, if you a lot of times you never move to the next stop or next point, your trace plot is going to stay at that point for a while. Super sticky, right? Super high correlation. Yeah, so overall, think is what for Gibbs sampler, very unlikely you're going to stay at the same point because every time you do a random walk, right? Whereas for Metropolis and later Metropolis Hastings as well, it's likely because you have this ratio of determining whether you're going to jump or not. And then if you do not jump, meaning that you just stay to your previous value, then you're going to have a sticky draw, and then of course high correlation, high autocorrelation. So that will be very typical when you run MCMC when Metropolis and Metropolis Hastings comes into play. So thinning, as well as like burn in, as well as run it longer, et cetera, all of those will be very important when you start to move away from Gibbs sampler. All right, so that's the general idea. So, well, here, rule of thumb, you should run it like really large number of times until it's converged. So pretty much, if you try to write it this by yourself, you start like a super large, I mean, like a long vector to store your parameter draws, right? And then you every time you keep running it, and then you save every iteration, and then later you might do some thinning, you might do some burning, and then trace plot as well as all correlation of the final draws that you have. All right, so features of the jumping distribution, we use J because it's jumping, but sometimes it's also called proposal distribution. It should depend only on theta S, but not any of the previous draws. Okay, so you, like say the normal draw and the normal example that I gave you here is centered at the current theta S. Okay, you wouldn't depend on any previous values. So you only depend on the current value they're working with. So that's important. And another important feature is it has to be symmetric. Okay, so that's why. So if you think about the normal that I just used here, let's see. This one here. Yeah. So we know that theta star is going to be random from this normal center at theta S and then with standard deviation C. So that in fact, because normal itself is symmetric, so we know that if you want to go back from theta star to theta S, it's the same jumping distribution. Okay, so that's a pretty important feature of Metropolis, and that's the biggest difference between this and the Metropolis Hastings that we're going to talk about as well. And another thing about this J jumping distribution is that must be that you can get to any value of the parameter space for theta from any theta S. So you just, well, this is sort of pretty vague, but pretty much this is trying to tell you that your jumping distribution should be flexible, that you wouldn't get stuck in one place, and then you will be able to fully explore the parameter space. Okay. Lastly, this is also pretty vague, must be such that you don't return periodically to any particular value of theta, so you never like go into a crazy loop kind of stuff, and then you never get out. But typically, if you put like a normal, or later the example I would give is a uniform, usually it's fine. Okay. But you might be guessing, okay, how am I supposed to pick the standard deviation for my normal jumping distribution, right? And that's actually a pretty important concept in all of the sampling here. Because if you pick a large standard deviation like C that I have for the normal, that means that every time you're jumping further away from your current draw, right? And so that's the large proposal steps. You can quickly move to posterior mode, but can get stuck for long periods because they're usually far away from the mode. But if you have small standard deviation, like C is small, then you're probably going to have high acceptance rate. So acceptance rate, sorry, I didn't explain it earlier. Acceptance rate is when you look at all of your chain, like the whole chain in the end, you're looking at how many times you get accepted to jump to the value that you propose. Okay. So if you're moving very small, then you could imagine, well, the posterior ratio of your current draw, or I should say the posterior ratio of your new draw over the current draw wouldn't be that big, the difference. The ratio might be close to 1, right? So it makes you more likely to jump, right? So when you have a small standard deviation for a jumping distribution, then you're going to have overall higher acceptance rate, but the moves are never large enough, so sometimes you can be highly correlated, that's one thing, and it can be steep. So choosing C is trial and error, and the general rule of thumb is for any Metropolis algorithm that you're running, you should try to achieve a 35%-ish acceptance rate. And the way that you're going to do it, for example, because that's only going to, so the only thing changes is the C, if you're going to using the normal proposal or jumping distribution. So you can do some tuning at the beginning. You can try some short runs and record the percentage of acceptance by changing different values of the jumping standard deviation. And then once you see, oh, okay, we sort of get about 30%-ish, then you can start running a longer chain. Because again, this can take a long time to finish, and then some short rounds as testing will be a good strategy. Okay. All right, so I've been talking about like all of these big ideas, so let's come back to normal model that we covered before. So this, again, you don't even need to do Metropolis system. You don't even need to do Gibbs sampler, because we know the actual full posterior, full conditional posterior distribution. But I just want to use this as an example that we can actually design a Metropolis algorithm here for this view. So this is the case that we have the normal models. The data model is normal. We fix the sigma, so it's known sigma. And we are putting a normal prior for mu to remember. Okay, and then we know the analytical posterior distribution is this crazy stuff in equation 6. And we know that we actually have all of those numbers. I mean, say the values of those theta 0, phi 0, mu 0, n, of course, phi, y bar, all that. So we can actually use Monte Carlo approximation to generate draws of mu. So again, all of the stuff that I'm going to talk about is not needed, but you can still try to design a Metropolis algorithm around this to see how you can play with your jumping distribution. All right, so the example that I'm giving here is using a uniform. Okay, so it's center at the current value you're doing. Okay, and C, the capital C here is the jumping step, right? The larger the C, the bigger, like the wider the interval they're drawing from, and then the smaller the C, like the narrower the interval that you're doing from this uniform. All right, so how are you going to do this? You're going to choose a new value mu star. I should say, not choose, generate a new value mu star from this distribution, and then we're going to calculate this ratio. Okay, this is, we know we have to get this ratio first and then determine whether we're going to jump or not. My question for you is, how are you going to compute this R? We know this is the formula, but in the context, what does it mean? We need the likelihood, right? We need the likelihood under the current value. That's in the bottom. We need the prior. So the prior we know is the prior, I mean, it's the normal mu 0, sigma 0, whatever that we have before, right? So the P mu star and the P mu S might be straightforward to do. The likelihood, again, you have a sequence of data points, right? And they're all IID, right? So you're going to do evaluating the density. So this is the time that you're going to use D norm. This D norm in R, not in just in R, is trying to evaluate the density probability. Okay. So compute it, it's this. That for the likelihood, I have to evaluate the density of each of the yi under my new draw of mu star, right? The sigma, which is given, and D norm for all of them, and then product them together. That's the joint density, joint PDF, okay, on the top. And then in the bottom is the joint PDF of yi, still the same sigma, but under different mu's. This mu, so because here we're generating, I mean, we're evaluating the density under this mu star, so that's why you fit in here. Okay. On the top, it's, oh, sorry, not mu star, mu s, and then mu star is what you go in here. Okay. And then the second here This is just evaluating the prior. Okay, so the prior, they're both normal. It's the same normal, I should say. But then the mu star and the mu s values are different, right? So the density, the probability density at the same prior might be different. So you need to use the d-norm function to estimate it. So these are the actual computation that should go into your head when you're thinking about computing R. And in practice, I should also mention that, well, we never actually got to deal with this in the whole semester, but if you start to do d-norm for a lot of observations and trying to product them, it's going to be super small. The computation is going to be very unstable in R. So typically you work on the log scale. Okay, so that's equation 10 is exactly like R, like how to compute R. But then equation 11 is on the log scale. The product becomes sum. Okay. But then you have this log R, which is just going to work just fine. Okay, so this will be much more stable. All right, so this is the sample script that you'll be able to do this if you ever want to try. So on the top, you see the log likelihood. So it's L-I-K, so it's log likelihood. And it's under the current mu. Okay, sigma is given. I'm doing d-norm. I'm doing d-norm on the log scale. So I choose log equals to true, right? So inside the sum, I'm evaluating the log density for each of my y. Okay? And then outside I do a sum. So that's the sum of all of the log likelihood. Okay? So that's my log likelihood, the joint log likelihood that I have. And then here in the loop, as you can see, that's what happens in each step of your MCMC for the Metropolis. Okay? So first of all, I generate a new value of mu. So I call it MUP. P stands for proposal. Okay? So it's from a uniform, right? So it's R unif. It's one draw from mu minus c and mu plus c. Okay, so that's exactly the uniform density that I mentioned earlier. And then I should also evaluate the log likelihood under the proposed mu, right? So that's what the second line in the loop is doing. It looks exactly the same, except now I have to evaluate at the mu p. Okay? So that corresponds to the equation that I showed you earlier. Okay. All right, so then log R is exactly also, I think, the equation I showed you before. It will be, because everything now is on the log scale, so dividing becomes minus, right? So we should do the log likelihood at the proposal value minus the log likelihood at the current value, right? So that's the first ratio that we talked about. And then the second, the third and the fourth terms here, they are just evaluating the prior density. Okay? Because prior, again, if you remember, is mu 0 and sigma 0. So I'm evaluating the prior density is a normal under mu p, and then minus that under the current mu. Okay? So this line completes my computation of log R. And then in the end, how to determine whether I'm going to jump or not. So R is the ratio that we're going to use. So typically in R, in the computing software, what you do is you're going to take a random, uniform between 0 and 1. Because ratio, without taking the log, R itself is a ratio. Right? So then if you take a uniform between 0 and 1, take the log, that becomes the same scale that you will be able to compare. So if your log R is larger than the random draw that you have, you're going to jump. Okay? So your mu becomes your proposed mu, your likelihood becomes the proposed likelihood, and also we have this scalar at the beginning that we initialize as 0 to record the acceptance rate. Okay? So every time if we jump, the ACCO is going to +1. So in the end, once you run the whole MCMC, you'll be able to know how many times out of, say, 10,000 iterations I have accepted my draw. And that is the thing. So ACCO divided by the total number of iterations, that's the acceptance ratio that I was trying to say that we should try to reach around 35%. So in practice, this is how it's done. So yeah, we never get to do it at all in our class, which is fine. But I think this is actually a pretty important topic in Bayesian methods and Bayesian inference, because Gibbs sampler are very nice, but they're very hard to come by. And because everything works under conjugacy, but just as we have been doing in JAX, if you want to be flexible and be creative in the way that you want to specify your priors, most of the time things won't be as nice with Gibbs that you can see, and then you have to rely on other computing schemes to do that for you. Okay. Right. So for the Metropolis testing, I'll just go really fast. And so now this is the time that jumping distribution is not going to be symmetric anymore. Okay. Symmetric sometimes may not be efficient and take a long time, meaning that it takes a long time for the chain to convert. And sometimes you might not want to have a symmetric jumping distribution. You want to be more flexible, like I want to favor the tail more than the other hand, for example, in the other side. So you might want to do non-symmetric, asymmetric, asymmetric, I guess, distribution of the jumping, and that's what we're going to do called Metropolis pasting, okay, M-H algorithm. So things work still similarly. If you look at the way that the Metropolis Hastings ratio, let me show you. What we had before, R, is only the first half of this ratio. Okay? And if you recall, so this part is the R that we computed for the Metropolis algorithm. Okay? Now we have to also consider the jumping, because previously the jumping is symmetric, so they cancel out. Okay? But now the jumping is not symmetric anymore. You will have to factor that into computing your ratio. Okay. So again, as you can see, if you know what the jumping distribution is, you will be able to use, like, say, maybe not d norm anymore, but like, say, I don't know, like a gamma, for example, so it's going to be d gamma, right? You're trying to evaluate the ratio under this too. So that's the key here. And let's skip this. And you might notice that Metropolis pasting is more broad. It's a broader, set of algorithms. So first of all, Metropolis is, because it's symmetric jumping, J theta star given theta S equals to the other direction. So Metropolis pasting is a special case of Metropolis is the special case of Metropolis pasting when J is symmetric. Okay, when they're symmetric, they get canceled out. And in fact, Gibbs sampler is also a special case of Metropolis pasting. So the target distribution is exactly the jumping distribution. Okay. So remember in Gibbs what we do, we just sample, like, say, we recognize what the distribution is, we use the previous or the current draws of the other parameters and just take it. And then for us, in this case, it's gonna be the same. The jumping distribution equals to target distribution. So Gibbs sampler never reject. We always keep going. Okay, so that's the case where alpha, the ratio that we compute, is 1. Anyway, so that's some fun facts if you're ever curious about them. So the example, well, again, I actually didn't write the part of the code because I thought it might be a good exercise, but we don't have time for that. But anyway, for the Metropolis pasting example, we come back to the normal, and then this will be the alpha that we have when we're doing Metropolis pasting. So you notice that, well, you start to have those you have to worry about, right? So we already worried about this before when we're dealing with the Metropolis, right? I show you how you can compute it. But now jumping distribution. So I'm giving an example of using a jumping distribution is not symmetric, a gamma. So it's centered. So the mean is mu s. So it's centered at the point. Okay. And I just put another value, fixed value for the second parameter. And then of course to compute it, you're gonna have one more term over here. Right? This term is the same as before. Okay? This term is the same as before, but now you have this j over j, right? Because I'm using jumping distribution as gamma, so that's how you're going to do it. Okay, use d gamma. And yeah, it's just getting a little bit even more complicated, but it's all really much the same thing. And I left this as exercise, so I didn't actually change the code to get you the Metropolis pasting algorithm. But if you're ever interested, you can try to change the code a little bit. So this is the Metropolis algorithm that we covered. If you want to change it to the Metropolis Hastings, feel free. And I post the script on Moodle under, so all of this are under Gibbs sampler and MCMC. Okay, so it's not the last topic, but a few back. All right, overall, Gibbs, so I should say JAX, what it's doing, I think, is that whenever they have a full conditional posterior distribution recognizable, then they're just going to do Gibbs, right? And so it's a big model where you have multiple parameters. Some of them might have full conditional posterior distribution recognizable, so you're going to use Gibbs. Okay? And some of them you might not be able to recognize them, so you can use either like a Metropolis or Metropolis Hastings, or there are actually many other possible algorithms out there that can help you to do MCMC sampling. So that's what I think JAX is doing. And if we go back to the beginning example that I tried to refresh your memory about. So for this model, mu and phi, we can use Gibbs step, right? And that's what I was asking in those questions. If you try to make the connection. And then beta k, we cannot recognize it, so you can use Metropolis or Metropolis to do that. And then once you have all of that, you have your complete MCMC. Okay? And that, in fact, can be coded by yourself. It is actually a fun exercise if you ever want to do it. But of course, you can always rely on JAX to do that for you. Okay? All right, so I think that's the end. And we're gonna, so before you go, I'm just gonna give back the midterm too. So the total is 55 points, and I think the mean and median both around 50, FYI. And I will make some appointments available if you want to do the corrections. Hopefully before the end of the semester, you can start. So that's all.